Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class. Welcome back to SIC2006. So the last lecture talked on the spin-spin coupling. So just want to touch on the labeling. Okay. In NMR, the letters far apart in the alphabet are typically called A and X, just to show that the nuclei are actually having very different chemical shapes. So they are labeled as A and X because A is quite far from the letter X. If the letters are close together, so you have this A and B system, so spin system. So they are used for nuclei with similar chemical shapes. So you can have this superimposed, very complicated. So that is called the AB spin system. But for these two lectures, we're going to just focus on the AX system. Okay, so I hope you have done that little exercise on the energy diagram so that you can understand the source of the spin-spin coupling. So that was for the AX system that we've seen before. And the spin-spin coupling results in a double of lines. And so now let's look at another, what we call spin system. So let's look at an AX2 system. So one of the proton, so you have two protons, but one in another environment it has two equivalent protons. Okay, so clearly that what you need to consider is the influence of the spin of the A nucleus on the resonance of the two equivalent HX and vice versa. So we're not now going to look at the energies diagram now, so we can sort of like imagine. Okay, so we have done the AX system, so then we know that for the two equivalent nuclei, it's the same as we have seen before, and clearly that what we can see that you have this a resonance which is split into three lines with the intensity of 1, 2, and 1, because this 2 is actually equivalent. So you're going to have this 1:2:1 splitting. For example, we have here an example of the AX2 system, the 1,1,2 trichloroethane. So here you have one, so this and this, the protons here and the proton here are clearly in two different environments. So, and this has two protons. So, and because of the two protons, so you see that you have the central the AX, the intensity for the X resonance of the AX2 system is twice as large as that of AX system. So you have the 1:1 here, and so for one of the peaks there, so you will see that you have the alpha alpha, beta beta, and alpha beta is going to be twice as large, and then you have here for this one proton here. Okay, and so you have here a doublet and you have here a triplet. So that's the A resonance, and you have here the X resonance. Now now let's look at an AX3 spin system. So here you have the methyl group, but this all the hydrogen are actually equivalent, okay, because of the rapid internal rotation. So you have one environment here and you have another environment here. We have three protons here, okay, so we know here this is going to give a doublet, right, the alpha and beta. But how about this? So because there are three protons. So you have the alpha, 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 the lowest energy, and you have at the extreme highest energy, the beta, beta, beta. In between, you have the alpha, alpha, beta, alpha, alpha, beta here. So you have beta, alpha, 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 beta, and alpha, beta, alpha. And you also have beta, beta, alpha, beta, alpha, beta, alpha, beta, beta. But all these are actually having the same energy, and this too. So that means in terms of intensity of the line, so this is going to be 3 times more intense than that of this. So that's why you have the 1, 3, 3, 1. Okay, so then you have a quartet. Okay, so you have a quartet here for the A resonance, and you have here, and of course the doublet here. Okay, so this is really looking at the what you call the splitting based on the neighbor. Okay, so like you're looking at these protons here. So this is based because the peak, the way the NMR is actually looking at, you know, what the neighbor, what is the splitting based on the neighbor. So you have one hydrogen neighbor here, so it is saying that, so you have that the spin, that the X resonance being a doublet. Okay, and the spin of this is because of this is saying this, okay, based on the spin of this. Okay, and usually the labeling is such that the A resonance is shielded. Okay, so this is going to be the 1331, and this is going to be the doublet based on what it says from its neighbor, the neighboring environment. So you see this 1 to 1, 1, 1, 1, 3, 3, 1. So that looks or sounds familiar. So really, truly, it is actually the intensity ratio is given by this Pascal's triangle. So, and this is only true when you're talking about spin half nucleus. If it's other than spin half, it will be something else, but we're not going to cover that. So in general, an equivalent spin half nuclei will split the resonance of a nearby spin or group of equivalent spins into n plus 1 lines with an intensity ratio given by that. So if there's no neighbor, so you will see only a singlet. If there's one neighbor, so you see a doublet, and if there are 2 neighbors, you see a triplet, and if there are 3 neighbors, you see the quartet, and so on and so forth. Okay, so this is it's not on the right, the figure, you know, below shows it's actually shows a 60 megahertz proton. So you have the CH3, CH2 cell. Okay, so clearly that this is the methyl group. Okay, the CH3 here. Okay, because of the neighbor is CH2, so N, remember the N plus 1. So the neighbor is the CH2, so 2 hydrogen, so 2 plus 1, 3, so you see the 3 peaks here. Okay, similarly, okay, this is the CH2 cell. It's going to be much deshielded because of the chlorine, which is electronegative, and it's seeing its neighbor, which is CH3. So 3 protons here, so 3 plus 1 is 4. So you have the 4 peaks here. So the 1, 3, 3, 1 intensity here. Okay. I also like to talk on this chemical equivalent. So if you have a group of nuclei, okay, they are chemically equivalent if they are related by symmetry operation of the molecule, and so because of that they will have the same chemical shift. Okay, and so here you have the methylene chloride. So you have an A2 system here. Okay, consists of only one line because the two protons are chemically equivalent due to symmetry, and so they have the same chemical shift. Okay, and if benzene as well will also contain one line because all the 6 protons are equivalent. The same reason, because they are chemically equivalent. The acetonitrile will also contain one line because all the meta are equivalent because of the rapid internal rotation. And the 1,2-dichloroethane and acetone will also show single line because of the two groups of the protons. The protons here are actually equivalent. So these are chemically equivalent. So there is a difference between chemical equivalence and magnetic equivalence. Chemically equivalent nuclei behave the same as one another chemically, but they do not have the same NMR properties as one another. Whereas magnetically equivalent nuclei are chemically equivalent and they have the same NMR properties. Okay, so if the nuclei under consideration do not have the same chemical shift, in other words, they are not isochronous. So isochronous means they have the same chemical shift. Then they are neither chemically nor magnetically equivalent. That makes sense if they don't have the same chemical shift. So they're definitely not chemically or magnetically equivalent. But all chemical or chemically or magnetically equivalent nuclei, they are actually isochronous. They have the same chemical shift. But however, need not be chemically or magnetically equivalent as their chemical shift may be identical by chance. So, example here, okay. So let's look at this. You will read this yourself, okay. So you see here the H4 and H6. They are magnetically equivalent because they have the same neighbor, right? H5. But H2 and H6, they are related via symmetry. So they will have the same chemical shift and the same coupling constant. Okay. However, so this is chemically equivalent. This is magnetically equivalent. Okay, via symmetry. Okay. So, however, they actually for the H2 and H6, they are coupled with different neighbors. So they may have the same chemical shift, but they're not magnetically equivalent because of having different neighbors. So, these are just, extra knowledge for you, because you may come across this term magnetically and chemically equivalent. You may wonder what they mean. So I hope that, this clear the waters. Okay. All right. So really a short lecture for this one. So look at these various types of AX system and understand the nature of this, that it follows this Pascal triangle n+1 rule, and so from there the chemical shift, the splitting is based on the neighbor, okay, based on the n+1 rule. Okay. All right, so that's it for this lecture. All right, thank you, and assalamu alaikum warahmatullahi wabarakatuh.